A spacecraft just flew through the atmosphere of a star, survived temperatures that should have vaporized it instantly, and found something moving inside that star's magnetic field that nobody predicted. Not aliens, not lava monsters, something stranger, zigzagging bursts of plasma that flip direction in a fraction of a second, and scientists still don't fully know why they exist. If you've ever wondered what's actually happening inside the sun, or thought we already knew everything about the star keeping us alive, you're about to find out how wrong that assumption is. Here's the thing everyone gets wrong immediately. People hear NASA sent a probe toward the sun, and their brain fills in a movie scene. A little metal ship diving into fire, melting like a candle, maybe punching through some fiery crust into a molten core. That image is completely false, and it's false in a way that actually makes the real story more interesting, not less. The sun doesn't have a crust. It doesn't have a surface you could land on, because it's not solid. It's a giant ball of plasma, which is basically gas so hot that electrons get stripped off atoms and go wandering around on their own. There's no inside to punch through in the way you're picturing. So when we say a probe went toward the sun, we need to be precise about what that actually means, because the reality is stranger than the fantasy. The spacecraft in question is called the Parker Solar Probe. NASA launched it in August 2018, and it's named after Eugene Parker, the physicist who, back in 1958, predicted the existence of something called the solar wind before anyone had proof it was real. That's worth sitting with for a second. A scientist did the math, said there's a constant stream of particles blasting out from the sun in every direction, and the scientific community basically said, prove it. Some of his contemporaries thought the idea was borderline absurd, that empty space couldn't possibly be filled with a continuous outward current of particles from a star. One journal reviewer reportedly rejected his first paper on the subject, and it only got published after a more senior physicist stepped in and overruled the decision. It took decades of spacecraft data to fully confirm he was right. NASA naming this mission after him was their way of saying, we're finally going to go check your homework in person while he was still alive to see it. Parker actually watched the launch and passed away in 2022, having lived just long enough to see his prediction get flown directly into the thing he theorized about. Now, the probe was never designed to touch the sun's so-called surface, because again, there isn't one in the traditional sense. What Parker Solar Probe is doing is flying through the sun's outer atmosphere called the corona. Yes, the sun has an atmosphere just like Earth does, except instead of nitrogen and oxygen, it's made of superheated magnetized plasma. And here's the detail that breaks people's brains every single time I bring it up. The corona is hundreds of times hotter than the visible surface of the sun sitting directly beneath it. The surface, called the photosphere, sits around 5,500 degrees Celsius. The corona, floating above it, reaches over 1,000,000 degrees. That's like standing next to a campfire and finding out the air 10 feet away is hotter than the flames themselves. It makes no intuitive sense, and for close to a century, physicists didn't have a solid answer for why it happens. This is called the coronal heating problem, and it's one of the biggest unsolved puzzles in solar physics. Parker Solar Probe was built specifically to fly into that mystery and gather answers no telescope from Earth could ever get, because you can't measure a magnetic field's fine structure from 93 million miles away. You have to go there. Before we get deeper into what it found, it's worth understanding why nobody attempted this sooner. Getting close to the sun sounds like it should be the easy direction to travel in space, since the sun's gravity is enormous and constantly pulling everything toward it. But that's exactly the problem. Earth is moving sideways around the sun at about 30 kilometers per second. To actually fall toward the sun, a spacecraft has to cancel out almost all of that sideways motion, and doing that takes an enormous amount of energy, arguably more than what's required to leave the solar system entirely. That's why Parker Solar Probe uses repeated gravity assists from Venus, 7 flybys total across its mission, each one stealing a little orbital energy from the planet to bend its path closer and closer to the Sun over several years. It's less like diving off a cliff and more like slowly tightening a spiral, trading altitude for speed one loop at a time. Engineers actually had to solve this as a fuel problem before they solved it as a heat problem, and that's a detail almost nobody talks about. The heat shield gets all the attention because it looks dramatic, but the orbital mechanics were arguably the harder puzzle to crack first. So let's talk about the how did it not melt question, because that's usually the second thing people ask. Right after, wait, it went inside the sun? The spacecraft carries a heat shield called the Thermal Protection System, about 11.5 centimeters thick, made of a carbon composite foam sandwiched between 2 carbon plates. On its closest approaches, that shield faces temperatures around 1,400 degrees Celsius, roughly hot enough to melt steel. But here's the trick, and it's a beautiful piece of engineering logic. Heat and temperature are not the same thing. The corona is incredibly hot, but it's also incredibly thin, meaning there are relatively few particles per cubic centimeter compared to something dense like air or water. Fewer particles hitting the shield means less actual heat energy transferred, even though each individual particle is moving at extreme temperature. It's the difference between sticking your hand briefly into a hot oven, which is survivable, versus sticking your hand into boiling water for the same amount of time, which absolutely is not, even if the oven air is technically hotter. Density matters as much as temperature. That's the engineering secret that let humanity build something that can survive grazing a star. There's a second layer of protection that rarely gets mentioned, and it's almost elegant in its simplicity. The heat shield faces the sun at all times, angled precisely, while every sensitive instrument, every wire, every delicate piece of electronics sits tucked directly behind it in the shadow the shield creates. Behind that shield, temperatures drop to something close to room temperature, around 30 degrees Celsius. The spacecraft isn't fighting the heat with brute force cooling systems. It's hiding from it, the same way you'd stand behind a beach umbrella instead of trying to individually cool every inch of your skin. If the spacecraft's orientation drifted even slightly, exposing unprotected components directly to the corona, the mission would end in seconds. That's why autonomous systems on board are designed to detect any dangerous tilt and self-correct without waiting for a command from Earth, because a radio signal takes over 8 minutes to travel from the sun's vicinity back to mission control. By the time engineers on the ground even noticed a problem, the spacecraft would already need to have fixed it or been destroyed. During its closest approaches, the probe goes essentially silent by design. It stores data instead of transmitting it in real time because there's no time and no safe way to spare the attention for a live broadcast while threading a needle past a star. Only after it swings back out to a safer distance does it turn its antenna back toward Earth and start downloading weeks of recorded data in a careful, patient trickle. And grazing is actually the right word, because Parker Solar Probe doesn't sit still near the Sunday. It's the fastest human-made object ever built. On its closest passes, it moves at around 690,000 kilometers per hour, which is somewhere near 430,000 miles per hour. At that speed, you could travel from New York to Tokyo in under a minute. During its closest approach on the 24th of December, 2024, the probe came within about 6.1 million kilometers of the sun's visible surface. That sounds enormous until you realize how big the distance from Earth to the sun actually is, about 150 million kilometers. So this spacecraft got roughly 96% of the way there, deep enough to be flying directly through coronal plasma, closer to the sun than any object we've ever built, by a huge margin. For comparison, Mercury, the closest planet to the sun, orbits at an average distance of about 58 million kilometers. Parker Solar Probe has now flown nearly 10 times closer to the Sun than Mercury ever gets. If you shrank the distance from the Sun to Earth down to the length of a football field, Parker Solar Probe's closest pass would put it about 4 yards from the goal line where the Sun sits. That's how close this thing actually got. Now here's where the actual discovery comes in, the thing referenced in the title, the something moving inside that changed everything. As Parker Solar Probe pushed through the corona, its instruments, specifically an instrument suite called fields, which measures electric and magnetic fields, started picking up something bizarre in the solar wind. Sudden, sharp reversals in the direction of the magnetic field, like the field was flipping itself inside out for a fraction of a second before snapping back. Scientists nicknamed these switchbacks because that's exactly what they look like on a graph, a zigzagging path instead of a smooth line. Picture a river flowing steadily in one direction, and then randomly, for a split second, a section of that river appears to flow backward before rejoining the main current. That's roughly the behavior we're talking about, except it's happening in a magnetized stream of charged particles moving at hundreds of kilometers per second, and it's happening thousands of times as the spacecraft passes through. This wasn't a slow, gradual realization either. The first close encounters happened in late 2018, just months after launch, and by the time NASA published the initial results in December 2019 in a set of papers in the journal Nature, switchbacks were already one of the headline surprises of the entire mission. Nobody had modeled the solar wind's near-Sun region and expected this specific, sharp, repeating kink pattern to dominate the data as thoroughly as it did. It's one thing to predict a phenomenon might exist in theory. It's another thing entirely to fly a spacecraft into the region and find that the phenomenon isn't a rare curiosity, but practically the default texture of the environment. What makes switchbacks especially strange is that they don't just involve the magnetic field flipping. When one occurs, the plasma itself gets a sudden kick in velocity, like the particles briefly speed up in that same jagged direction. Some individual switchback events last only seconds. Others stretch out over minutes or longer, and they don't appear randomly scattered. They tend to cluster into patches, groups of switchbacks bunched together, separated by calmer, quieter stretches of solar wind in between. That patchiness is a clue in itself. It suggests these events are tied to specific structures at their source, rather than being some smooth, continuous background noise happening everywhere at once. These switchbacks aren't just a cool visual anomaly. They matter because they might be a missing piece in two of the Sun's biggest unsolved mysteries at once. Mystery number one, the coronal heating problem I mentioned earlier, why the corona is so much hotter than the surface below it. Mystery number two, why the solar wind accelerates outward the way it does, reaching speeds that older models struggled to fully explain. One leading idea is that these switchbacks are the fingerprints of a process called magnetic reconnection, where magnetic field lines near the Sun's surface snap, cross, and reconnect in new configurations, releasing bursts of energy in the process, a little like a rubber band snapping and flinging energy outward when it breaks. If that's what's generating these switchbacks, it could mean the Sun is releasing energy in small, constant, almost sneeze-like bursts across its entire surface, rather than through a few large, dramatic events. Multiply millions of these tiny energy releases across the whole Sun, and you might have your explanation for both an overheated corona and an accelerating solar wind. That's the theory. It is not proven fact yet, and I want to be very clear about that distinction, because a lot of headlines blur the line between scientists found a strong clue and scientists solved the mystery. We are firmly in clue territory, an extremely exciting clue, but a clue. There's actually a specific location scientists suspect might be generating these switchbacks, and it involves structures called funnels. small magnetic channels rooted at the boundaries between what are known as supergranules, essentially convection cells on the sun's surface, each one roughly the size of a small country, constantly bubbling and shifting like the surface of boiling water, except on a planetary scale. At the edges where these convection cells meet, magnetic field lines get squeezed, twisted, and stressed. Some researchers think switchbacks are born right at these boundary funnels, snapping into existence as the magnetic field there gets tangled past its breaking point and violently reorganizes itself. If that turns out to be correct, it means the birthplace of the solar wind isn't some smooth, uniform region. It's a chaotic, boiling patchwork of magnetic knots constantly untangling themselves, and switchbacks are the visible aftermath, like watching sparks fly off a badly frayed wire. Let's return to that misconception for a second, because it's worth hammering home. The sun did not have something moving inside it in the sense of an object, a structure, or anything solid. What moved were magnetic field lines and charged particles, invisible forces behaving in a way physics didn't predict. That might sound like a letdown compared to the mental image of some mysterious shape swimming around inside a star, but honestly, I'd argue the truth is cooler. We're talking about a star's magnetic architecture rearranging itself in real time, whipping plasma around at extreme speeds, and a robotic spacecraft flying directly through that chaos to record it happening. You don't need aliens inside the sun when the actual physics is already this dramatic. It's worth pausing here to separate switchbacks from something people often confuse them with: solar flares and coronal mass ejections. Those are much bigger, much more violent events, sudden explosive releases of energy from the sun's surface that can hurl billion-ton clouds of plasma across the solar system in hours. Flares and coronal mass ejections are the sun shouting. Switchbacks are more like the sun's constant background hum, a steady murmur of small-scale magnetic snapping happening everywhere, all the time, in the quiet spaces between the big dramatic outbursts. Both phenomena involve magnetic reconnection at their core, but they operate at wildly different scales, and conflating them is one of the easiest ways to misunderstand this story. If a coronal mass ejection is a volcano erupting, a switchback is more like the constant, quiet cracking and shifting of tectonic plates that never makes the news but is happening underneath your feet right now, regardless. Let's slow down and build the bigger picture, because understanding why this matters requires knowing what the solar wind actually is and why we care about it beyond pure curiosity. The sun is constantly ejecting charged particles, mostly electrons and protons, in every direction at speeds ranging from around 300 kilometers per second for what's called slow solar wind, up to 750 kilometers per second or more for fast solar wind. This isn't a one-time event. It's continuous, a permanent outward exhale from our star that fills the entire solar system with a thin, fast-moving plasma. Earth sits inside this stream, and our planet's magnetic field acts like a shield, deflecting most of it. When that shield gets hit by a particularly strong burst, usually from something called a coronal mass ejection, a huge eruption of plasma and magnetic field from the sun's atmosphere, we get geomagnetic storms. Sometimes that means beautiful auroras dipping down to lower latitudes than usual, something we actually saw dramatically in May 2024 when a series of powerful solar storms pushed auroras visible as far south as parts of Florida and northern Mexico, places that almost never see them. Sometimes it means disrupted satellites, GPS errors, radio blackouts, and in extreme cases, damaged power grids. In 1859, an event called the Carrington event was strong enough to set telegraph systems on fire in some locations. If something on that scale happened today, in a world completely dependent on satellites and electronics, the disruption would be massive potentially costing economies billions of dollars and knocking out power for extended periods across entire regions. So understanding exactly how the solar wind forms, accelerates, and behaves isn't just academic. It's directly tied to protecting the infrastructure modern life runs on. Every switchback, every magnetic anomaly Parker Solar Probe records feeds into better models for predicting space weather, the same way meteorologists predict storms on Earth, except this storm system is 93 million miles away and moving at hundreds of kilometers per second. Think about how much of daily life quietly depends on satellites functioning normally. Bank transactions rely on precise timing signals from GPS satellites. Airplanes navigate using them. Farming equipment uses centimeter-accurate positioning to plant crops in efficient rows. Shipping fleets cross oceans guided by them. None of that is obviously connected to the sun in most people's minds, but all of it sits downstream of space weather, and space weather sits downstream of exactly the kind of physics Parker Solar Probe is trying to decode. This isn't a mission that only matters to astrophysicists in a lab. It's a mission that feeds directly into forecasting models meant to give power grid operators and satellite companies advance warning before a serious solar storm arrives, the same way hurricane forecasts give coastal cities time to prepare. I want to come back to the misconception one more time, because there's a second layer to it that's just as common. Some people assume that because the corona is hotter than the surface, that must mean something is actively burning hotter up there, like the atmosphere is somehow more on fire than the star itself. That's not quite right either. The sun's energy is generated in its core through nuclear fusion, hydrogen atoms slamming together under extreme pressure and forming helium, releasing energy in the process. That energy works its way outward over an incredibly long time, sometimes estimated at thousands of years, for a single photon to random walk its way from the core to the surface, bouncing around inside dense plasma the whole way, constantly absorbed and re-emitted in random directions, like trying to walk in a straight line through an infinitely crowded room. By the time that energy reaches the visible surface, most of it radiates away as light and heat, cooling to that comparatively modest 5,500 degrees Celsius. The corona's extreme heat isn't leftover fusion energy blazing hotter. It's a separate heating process happening in the outer atmosphere itself, something added on top of what naturally radiates from below, and that separate process is exactly what remained unexplained for so long, and exactly what switchbacks in magnetic reconnection might now be helping to explain. Two totally different heat sources, one confusing headline number that makes people think the sun works backward. It doesn't work backward. It just has an atmosphere behaving in a way we're still learning to fully model. Here's the deeper scientific twist I promised, the part that even people who've heard about Parker Solar Probe often miss. Switchbacks weren't actually a total surprise the very first time they showed up. Earlier spacecraft, including one called Ulysses back in the 1990s, had spotted hints of similar magnetic kinks in the solar wind, but only occasionally and only far from the sun, where the signal was weak and easy to write off as noise. What changed everything with Parker Solar Probe is that once it got close enough to the sun, inside a region much nearer to where the solar wind actually originates, these switchbacks stopped being rare oddities and turned out to be everywhere. Dense, frequent, almost like the default state of the solar wind close to its source, rather than some occasional glitch. That completely reframes the mystery. It's the difference between spotting a strange footprint once in a forest and thinking it might be nothing, versus finding thousands of the same footprint clustered together and realizing you've been walking past the source the entire time without knowing it. The switchbacks aren't a rare side effect happening somewhere out in space. They appear to be a fundamental part of how the solar wind is born, right at the base of the corona, and that changes how physicists have to think about the whole system. Parker Solar Probe isn't working alone out there either, and that's worth knowing. because science rarely advances from a single data source. The European Space Agency launched a companion mission called Solar Orbiter in 2020, which takes a different approach, staying farther from the sun but carrying cameras capable of directly imaging the solar surface and poles in ways Parker's solar probe, buried behind its heat shield, simply cannot. Solar Orbiter has captured some of the closest true images ever taken of the sun, revealing small-scale eruptions nicknamed campfires, miniature flares far smaller than typical solar flares, potentially connected to the same coronal heating puzzle. Combine that with NASA's Solar Dynamics Observatory, which has been watching the sun continuously from Earth orbit since 2010, and you get multiple spacecraft essentially triangulating the same star from different angles and distances, cross-checking each other's data. When Parker's solar probe detects a burst of switchbacks in the solar wind, scientists can sometimes trace that event back to visible activity Solar Orbiter or the Solar Dynamics Observatory captured happening on the surface days earlier, connecting cause and effect across millions of kilometers of space. It's a bit like having security cameras at 3 different distances from a crime scene. One camera captures the wide shot, one captures a medium view, and one Parker is basically standing in the room where it happened. Together they can reconstruct a story none of them could tell alone. There's another discovery worth mentioning because it connects to a completely different old assumption. For a long time, scientists predicted there should be a dust-free zone very close to the sun, a region where the star's heat and radiation pressure would be intense enough to vaporize or blast away any tiny dust particles drifting through the inner solar system, leftover debris from asteroids, comets, and the formation of the solar system itself. Parker Solar Probe's imaging instrument, called WHISPER, has been gradually detecting a drop-off in dust density as it gets closer to the sun, generally consistent with that predicted zone, though the full boundary and its precise edge are still being mapped and confirmed through ongoing passes. It's a smaller story than the Switchbacks, but it's a nice reminder that this mission isn't just chasing one headline discovery. It's systematically testing a whole list of decades-old predictions about our star, some of which are holding up and some of which are getting revised in real time. There's also an instrument on board called SWEEP, short for solar wind electrons, alphas, and protons, and its job is almost comically direct for a spacecraft flying this close to a star. It literally catches solar wind particles as they slam into the spacecraft and measures them directly, their speed, their temperature, their density, their composition. Most instruments in astronomy work by observing light from a safe distance and inferring properties indirectly. SWEEP doesn't infer anything. It's tasting the sun's exhaled breath directly as it rushes past, which is about as close to physical contact with a star as any instrument humans have ever built has gotten. Between SWEEP catching particles directly and fields measuring the magnetic environment those particles are embedded in, Parker Solar Probe effectively has both a stethoscope and an MRI machine pointed at the same patient at the same time, which is exactly why the switchback discovery came together as clearly as it did. One instrument saw the magnetic kink. The other confirmed the plasma was physically moving in response to it. Together, they turned a strange squiggle on a graph into solid physical evidence of something real happening in the plasma itself. Let's talk about what scientists still genuinely do not know, because a good science story doesn't pretend everything's wrapped up with a bow. We don't yet have a complete, confirmed model explaining exactly how magnetic reconnection near the sun translates into the specific frequency, size, and behavior of switchbacks we're now seeing at close range. We don't fully know whether switchbacks are the primary driver of solar wind acceleration, a major contributor, or one piece among several unknown mechanisms working together. We also don't have a complete answer to the coronal heating problem itself. Switchbacks and reconnection are strong candidates but there are competing and possibly complementary theories involving things like plasma waves, called Alfvén waves, which are oscillations traveling along magnetic field lines and might carry energy upward into the corona as well, like plucking a guitar string and watching the vibration travel down its length. It's entirely possible the real answer isn't one clean mechanism, but a combination, reconnection here, wave heating there, working together in ways we're still mapping out pass by pass. Parker Solar Probe is scheduled to continue making closer and closer approaches, using Venus flybys to gradually tighten its orbit, with its final planned closest approaches bringing it to roughly 6.1 million kilometers from the Sun's surface, the closest a human-made object has ever traveled to a star, continuing to gather data through the mission's extended operations. Every one of those passes is another chance to either confirm or completely upend current theories. And honestly, upending old theories tends to be where the field jumps forward the fastest. It's also worth admitting there's a limit to how far even this incredible engineering can take us. Parker Solar Probe will never physically touch the visible surface of the Sun, and it was never meant to. Even at its closest, it's still sampling the outer corona, not the churning layer below it. Some questions about the deepest processes driving the Sun's magnetic field, generated by convection and rotation far beneath the surface in a process called the solar dynamo, remain almost entirely inferred rather than directly observed, pieced together from surface behavior, magnetic patterns, and helioseismology, which is essentially using sound waves rippling through the Sun to map its interior the way doctors use ultrasound to see inside a human body without cutting it open. We are extraordinary at indirect detection. We are still extremely limited when it comes to anything resembling direct access to a star's interior, and that gap is going to remain open for a long time, maybe permanently, given the physics involved. There's a wider lens worth putting on all of this before we wrap up, because it's easy to treat the Sun as a special case, our star, uniquely deserving of study just because we happen to live near it. But every discovery Parker Solar Probe makes about our Sun becomes a working model for understanding stars across the galaxy. Every star with a magnetic field likely produces some version of a stellar wind, and stars far more active than our Sun, especially young, small, red dwarf stars, tend to have far more violent flares and far stronger stellar winds. That matters enormously for the growing search for habitable exoplanets, because a planet sitting in the so-called habitable zone of its star, at the right distance for liquid water, can still get its atmosphere stripped away entirely if that star's wind is aggressive enough. Mars is actually a working example of this in our own solar system. Evidence gathered by missions like NASA's MAVEN spacecraft suggests Mars once had a thicker atmosphere and possibly stable liquid water on its surface, before losing much of that atmosphere over billions of years, partly because Mars lacks a strong global magnetic field to deflect the solar wind the way Earth's does. So understanding exactly how our own Sun's wind forms and behaves at its source isn't just a curiosity about our specific star. It's a rehearsal for evaluating the habitability of thousands of other planets orbiting thousands of other stars we're only just beginning to study in detail. Looking further ahead, this mission doesn't exist in isolation. NASA launched another mission called IMAP, the Interstellar Mapping and Acceleration Probe, designed to study the boundary where the solar wind eventually collides with the wider interstellar medium, the thin gas and dust that fills the space between star systems. Combine that with Parker Solar Probe studying the birth of the solar wind up close, and Solar Orbiter and the Solar Dynamics Observatory watching the surface that generates it, and you start to see an entire fleet of spacecraft assembling a complete life story of the solar wind from the moment it's born in a tangled magnetic funnel near the Sun's surface, all the way out to the edge of where our star's influence finally fades into the rest of the galaxy. That's not one mission solving one mystery. That's an entire coordinated effort to understand a river of particles from its source to its mouth, stretched across billions of kilometers of space. Step back for a second and consider what's actually happening here. We built a machine, launched it off our planet, and asked it to fly through the atmosphere of the nearest star, close enough to be scorched by heat that would vaporize almost anything else humans have built, all so we could measure the invisible zigzagging of a magnetic field we can't even see with our own eyes. That's not science fiction. That's a mission that has already happened, is still happening, and is still sending data back. The sun isn't some static yellow ball hanging in the sky providing light and warmth on autopilot. It's an active, violent, constantly shifting magnetic system throwing off storms of particles every single second, and we are only now, in the last few years, getting close enough to actually watch that process happen in real time instead of guessing at it from 93 million miles away. So the next time someone tells you a probe went inside the sun, you'll know exactly what that really means and exactly how much cooler the true version is than the myth. Nothing melted, nothing that shouldn't have survived did, and nothing alien was swimming around in there. What we found instead was proof that even the object we've stared at every single day of our lives, the one thing in the sky humans have never stopped watching, still had secrets folded into its magnetic field, waiting for something fast enough, tough enough, and close enough to finally notice them moving. We spent centuries staring at the sun from a distance, thinking we understood it, and it took one spacecraft flying directly through its fire to prove we'd barely been looking at all.